Hey there y'all, Mr. McMillan here. We're going to look at Unit 1 on quantities and expressions today, and then Section 1.1, precision and significant digits. And so follow along in your notes, either on paper or in your OneNote app. So our objective for today is that you'll be able to identify the most precise measure and write answers to arithmetic problems using significant digits. Our one standard for today is in Q3, which is to choose a level of accuracy appropriate to limitations on measurement when reporting quantities in context. So today we're going to talk about what level of accuracy we have and also what it means to be precise using significant digits. Okay, so the first definition we need to look at here. Precision is the level of detail of a measurement. So again, precision is the level of detail of a measurement. And so when we think about what we mean by detail, think about if you're trying to measure a football field. You know, we could measure it in yards like it normally is, right? We can measure it in feet. We can measure it in inches. We can measure it in miles. But which one would give us the best detail, right? Like, let's say that football field's not perfect. Which one would give us the best idea that it is off? Would we measure it in miles? No. We would measure it in the smallest units. We would measure it in inches. Now, it would be a lot of inches to measure a full football field, but it would be the more precise measurement of that field. All right, so let's look at example 1. We want to talk about which one is more precise in the pair. And remember what I just said. We're looking for either the smaller unit or the one that allows us to get to smaller scale. And so our first unit is 5.7 meters, or our second unit is 568 centimeters. So when we think about a meter, right? Meter is about 3 feet, and a centimeter, remember, is very small. And so which measure is more precise? It's the centimeters. Now, there are going to be exceptions to this case when we look at units themselves, and we'll look at some of those examples later on. But the key is this, understanding, especially in scientific units, so not our American units like inches and miles, but using the scientific units of meters and grams and liters and such. We have to check our decimal places and understand which one is more precise than the other based on those values. And sometimes it makes sense to convert one to the other. And so I could convert this 568 centimeters to 5.68 meters. And this is 5.7 meters. And so which one's more precise? Well, if they have the same units, we're going to look at which one has more decimal places. And so this only goes to the tenths. This one goes to the hundredths. So the more precise is the one that goes to the hundredths. Look at example B. And so based off what we just said, which one do you think is more precise in the pair? Is it 31 ounces or 31.32 ounces? Take a look at that one. All right, so which one is it? Well, this one has only whole ounces. This one gets us to the hundredth of an ounce, and so this is our more precise unit. So let's take a look at these other examples here. You should have 3 examples here to try out. So pause the video for a second and try these 3 examples. And then, again, think about which unit is smaller in scale. So pause the video now. All right, now that you've paused the video and tried these 3 problems, let's look and see how you did. In example 1, 2 pounds or 31 ounces. They're both in whole units, so which unit is smaller? Is a pound or an ounce smaller? Well, it's the ounce. So the 31 ounces is more precise than just 2 pounds. 9 inches or 1 foot. Look at example 2 now. Is 9 inches or 1 foot more precise? Well, it's the 9 inches. And finally, the 6.77 meters or 676.5 centimeters. Which one of those two is more precise? And there's actually 4 examples here, so make sure you got that 4th one down there. Which one of those two is more precise? Well, again, this is like the first example we looked at. We want them to be in the same units. And so remember how to convert from centimeters to meters. You should remember that from middle school. So our meters here, 5.77 meters. to go from centimeters to meters, we're going to move that decimal place twice. So 6.765 meters. And again, we look at which one has more decimal places, which one goes further in the decimal. And so this one would be the 676.5 centimeters, or 6 and 765 thousandths meters. Last example, 1 mile or 5,280 feet. Which one's more precise? They're the same length because 1 mile is 5,280 feet, but that's not what we're asking. We're asking which one's more precise. If I measure in feet, it's more precise because a foot, small unit. Big unit for a mile. All right. Let's talk about significant digits. Significant digits are the digits in a measurement that carry significance about the precision of a measurement. So again, significant digits are the digits in a measurement that carry significance or meaning. That's another word that we could use there. Meaning about the precision of a measurement. And so we have 5 rules when it comes to significant digits, and we're going to do some examples with these that you'll fill into your notes. So case 1 is that all non-zero digits are significant. So if I have the number 325, how many significant digits does it have? Well, the 3, the 2, and the 5 are all significant, and so this would have 3 significant digits. Okay? If I had the number 4.21, again, all non-zero digits are significant. So how many digits are significant? Again, it is 3. So this has 3 significant digits. Okay? Now, let's talk about case 2. Case 2 says that zeros between 2 other significant digits are significant. So again, zeros that are between 2 other significant digits are significant. Now, some zeros will be significant later on as we look through cases 3 through 5. Okay? But in this case, let's look at just ones that have non-zero numbers in between. So if I have the number 2.04, right? The 0 in the middle here, and I know I'm putting my hand in front of that camera, so excuse me for that as I write on the screen. That 0 in the middle is going to be significant because it's between 2 non-zero numbers, the 2 and the 4. So this would have 3 significant digits. Now, what about a number like 400 or 4,091? Again, the 0 there is between 2 significant digits. And so how many significant digits would be in this number? The 0 would be included, so this is 4 significant digits. Okay? Case 3, zeros to the right of the decimal point and at the end of a number are significant. So let's talk about where we're talking about these numbers. These are, so we got the decimal point, and we're talking zeros that are at the end of the number way over here, right? And so we'll have like 0.459200. So let's do that, 0.459200, okay? And well, let's not start with a 0. Let's make this an 8 in the front for the moment. We'll talk about that 0 that leads in a minute. So 8.459200. All those non-zero numbers are significant, right? But when we get to those zeros at the end, oops, these zeros here, are they significant? Well, they're to the right of the decimal, and they are at the end of a number. And so all those digits are significant, and so this is going to have 1, 2, 3, 4, 5, 6, 7 significant digits. Okay? And so it doesn't matter how many decimal places we have there, any zeros at the end of a number are significant. Okay? Let's look at case 4. Zeros to the left of the first non-zero in a decimal are not significant. Again, zeros to the left of the first non-zero digit in a decimal are not significant. So if I have the number 0.0001, okay, we started with a 0, so that 0 is not significant typically, okay? And we'll talk about why or why not it might be in certain cases. But this leading 0 here is not significant, okay? Which means that these next 3 zeros here, these zeros here, and also this one here, the one that we were talking about leading, all of those are not significant. So how many significant digits do we end up with? Well, we end up with just the 1. And so this would only have, come on, click it, there we go, 1 significant digit. Okay, and so we can do one more number. We can do, let's say, 0.2040. Well, we need, let's put the decimal here. So 0.0240. We'll just erase that there. Okay, so 0.02040. So let's combine a few rules here now. We're trying to get a little tricky, right? So think about which zeros are going to be significant and which zeros are not. And so when we look through here, these zeros are insignificant. They're not significant, right? The 0 between the 2 and the 4, of course, that goes back to rule 2, right? Zeros between two significant digits have to be significant. So that 0 is definitely significant, right? Because it's between a 2 and a 4. And then we look at the 0 at the end. Well, that goes back to case 3, right? Zeros to the right of the decimal and at the end of the number are significant. So this 0 is significant. And so when we look at that case, how many significant digits does it have? We started the 2, 1, 2, 3, 4. This has 4 significant digits. Okay? And so we look at case 5, the last case here. Zeros at the end of a number without a decimal point are assumed to be not significant. Zeros at the end of a number without a decimal point are assumed to be not significant. So we're talking about really large numbers here. We're talking about like if we have like 4,920,000. Okay? 4,920,000. All those zeros at the end of the number, okay? So all of these are going to not be significant because once I get past the last non-zero number, and I don't have a decimal place in the number, so it's just a whole number, right? Or an integer, technically based on the sign, right? The only numbers that are going to be significant are those 3 digits there. So this has 3 significant digits. And if I had a 0 in the middle, like if it was 4,020,000, right? So let's say that number, 4,020,000, right? Well, the 0 in between the 4 and the 2 is still significant because it's between 2 non-zero numbers. And so this would still have 3 significant digits. Does that make sense? I hope that makes sense with those 5 cases. All right, so we're going to take a second. We've talked about a lot of cases here. You're going to look now at a couple of examples, okay? So how many significant digits are in 840 and 90 thousandths meters? Think about all those cases we just talked about. Which zeros are going to be significant? Which zeros are not going to be significant? Well, in the number 840 and 90 thousandths, this 0 is between 2 non-zero numbers, right? Because you got the 4 on the left, the 9 on the right. So both of these zeros in the middle are significant, right? So that goes back to case 2, right? That zeros in between non-zero numbers are significant. And then the 0 at the end, it's to the right of the decimal and it's the end of the number. So any zeros at the end are significant, right? So all the zeros are significant. All the non-zero numbers are, of course, significant. And so I've got 3 and 3, that makes 6. So this has 6 significant digits. Okay? Example B. Determine the significant digits in this number. This is 235 millionths grams. Think about what zeros are significant and what zeros are not significant in this number. How many significant digits does it have? Well, all those zeros in the front, they're not between non-zero numbers. So they are not significant. all of these are not significant. So the only numbers that are significant are the non-zero numbers at the end, the 235. And so that's going to leave us with 3 significant digits. Okay, so that's where we're at. So let's look at a couple examples here. You've got 3 examples here. Determine the number of significant digits in each measure. So pause the video for a second, try these 3, and then come back. All right, so let's look at number 4, 36,000 feet. What is significant here? Well, the zeros at the end are not significant. That goes to case number 5, right? So the zeros at the end of a number that doesn't have a decimal, all those zeros at the end are not significant. And so this only has the 36, right? This will be 2 significant digits. 0.01, 1/100th of a kilogram. How many significant digits? So it is, these zeros are not significant. And so this will only have 1 significant digit. Example 6, 15.0 liters. Is that 0 at the end significant or not? Well, it's to the right of the decimal. It's also to the right of something significant. So is that 0 significant? You betcha. And so this has 3 significant digits. All right, we're getting to the end here. We're going to talk about operations of significant digits for a second. When you perform the calculations with measurements of differing precision, the number of significant digits in the solution may differ from the number of significant digits in the original measurement. So we might be taking a number that has 2 significant digits and a number that has 3 significant digits, and the answer could potentially have 4 significant digits. It just is based on the rules that we see below. And so here's the rules. For addition or subtraction, because remember subtraction is just the inverse of addition, the sum or difference must be rounded to the same place value as the least significant digit of the least precise measurement. Okay, so again, rounded to the same place value as the least significant digit of the least precise measurement. Okay, and so let's talk about what that means. If I add 3.4 and 4.52, I will add those two numbers together like I normally do, and I will get 7.92. But which number is less precise, the 3.4 or the 4.52? Well, it's the 3.4. This is my less precise value. So I will round it to the place value of the least precise measurement. So I'm going to round it to the 10th place, which means that this answer is 7.9 when we consider significant digits. Okay? Same would work for subtraction. Again, you're going to take the least precise measurement and round it to that place. Okay. Multiplication and division. It's a little different. The product or the quotient must have no more significant digits than the least precise measurement. So again, the product or the quotient must have no more significant digits than the least precise measurement. And so what that means is this. If I have 3.4 and I'm multiplying it by 4.52, okay? Again, I'm going to look at which one is the least precise measurement. Well, that's the 3.4 still, right? But now I don't say what's the place value. I say that this has 2 significant digits, which means my final answer can only have 2 significant digits. And so when I multiply this out, and we could do the calculation, do it in your calculator, or do it by hand, whichever way you want to do it, but I'm going to pause for a second, get the calculator, and then put the answer here. All right, so that answer is 15.368, 15.368. And so remember what the rule said. It said that I'm going to round this to only have the number of significant digits of my less precise measurement. And so my final answer can only have 2 significant digits, and that's counting from left to right. And so 1, 2, I will look next door to the neighbor. The neighbor is a 3. So this final answer, rounded to the appropriate place with significant digits, is just 15. I know it sounds crazy, but that's the rule. All right, so last example we're going to look at is dealing with a rectangular garden. We're going to talk perimeter, we're going to talk area. Okay, so find the perimeter of the garden using the correct number of significant digits. So remember, how do we find perimeter? If I've got a rectangle, right, and this is 16 feet and this is 23.6 feet, obviously my drawing is not to scale. Remember, perimeter would be adding up all the sides, so this other side would also be 16 feet, and this side would be 23.6 feet. When we add those together, 32, and this is going to be 47.2, so 32 and 47.2 is going to give us 79.2 feet. So as we look at the perimeter here with the correct number of significant digits, remember we're going to take the place value of the least precise measurement, and that is the 16 feet in this case. And so we'll round this to the whole number. And so with the correct number of significant digits, this is 79 feet. Now to find the area, remember that is length times width. Area is length times width. And so we're going to take our 16 and multiply it to the 23.6. And so when we do that with our calculator, we get 377.6 square feet, or feet squared. And so rounding again, remember we're going to take with multiplication or division the least precise measurement and the number of significant digits that it has. So our least precise measurement is still this 16, but it has how many significant digits? 2 significant digits. So our final answer can only have how many significant digits? 2. So 1, 2, we look next door for rounding. The 7's going to round us up, so it's going to be 380 square feet with the appropriate number of significant digits. So why must the area have no more than 2 significant digits? Well, it goes to that least precise measurement. So we look at our two measurements, right? Which one is less precise? This one is less precise because it's to the whole number. This one's to the 10th place. And so if we had numbers that were flipped, so if we said, let's say we had 10.6 and 0.02, right? 0.002. And so the less precise number would be the 10.6. It'd have 3 significant digits, whereas the other one only has 1. And so we've got to pay attention to those cases in the end. All right, so that is the, oh, we got one more question here. Can the perimeter of a rectangular garden have more significant digits than its measure of its length or width? And so think about that for a second. Pause the video and just take a second to think. Can the measure of a rectangular garden have more significant digits than the measure of its length or width? And so the answer is yes here. And it, again, depends on our values. Let's take, for example, this. If I add, okay, we're talking about the perimeter here, right? So if I have, let's say I have a 2 foot by 4 foot rectangle, right? And I take the perimeter. Well, 2 plus 2 is 4, and 4 plus 4 is 8, so 8 and 4 is 12. This would be 12 feet, right? Well, I round it to the least precise place value. Well, they're both to the whole number, so I'm rounding to the whole number. So I keep this. So that is one example of where I will end up with a number with more significant digits than the add-ins that we have. Okay, I'm not going to ask us to do the your turn there. We'll do those in class, but that's what we'll look at when you're here tomorrow. So again, I hope you've taken your notes well. Make sure you fill out that Google form. You'll answer a couple questions there based on the examples and based on what questions you have, because remember, you're going to put in any questions you have from this video into that Google form. So make sure you get that filled out. I hope you all have a great day, and I will see y'all tomorrow.